Okay, so the last topic we're talking about today is something called a heating curve. Well, a heating curve is going to be a very useful tool for the next set of notes when we are determining the amount of energy that is required to heat something through multiple phases, multiple states of matter. And you'll understand that more later after you've seen those notes. But it's important before we use these heating curves to first know how they work, know what they are. So looking at this curve, I want you to recognize the axes. The y-axis is temperature in degrees Celsius. So, and then the time, you could also label this as heat. So we're heating something up. And the longer the amount of time is that it's sitting on a burner or whatever, the more heat energy is being absorbed by whatever this is that we're heating up. Okay, this is a phase change diagram, a phase change heating curve. Okay, and I hope that you recognize as we heat this substance up that overall the temperature is increasing. That should make sense. Okay, that should make sense that as I heat it up, the temperature increases. But you see that it will increase and then it levels off, and then it increases again and it levels off again and it increases again. That's because we have some phase changes taking place. We start with the lowest energy state of matter. Think about what that would be. Hopefully you can recognize it. The lowest energy state of matter in section AB right here is solid. And then it changes from a solid to, in section CD, a liquid. And then in this last section, EF, we have gas. Okay, there's your three states of matter. But what are those other two things? What's this line right here? That line for BC. And the line for DE. Well, those lines, those flat lines, that's where the phase change is occurring. So as we're heating this substance up from A to B, the temperature increases until it reaches a point at which a phase change can occur, going from solid to liquid. So in section BC, we have two states of matter. We have solid and liquid. And in section DE, we have liquid and gas. Because that is where the phase change is occurring, between solid and liquid, and between liquid and gas. So let's talk about those phase changes. I want to label them. The solid to liquid phase change would be right here from B to C. Let's number that as 1. Okay, so phase change 1, as in going from solid to liquid, we know that that's called melting. I want you to also write down a name for it we're going to be using later, fusion. Not nuclear fusion, but melting has another fancy name, and that's fusion. Okay. Now melting, I'm increasing the heat. I'm having to, it has to absorb energy, absorb heat in order to occur. So that is an endothermic process. Okay, now let's look at the next one. So it says 2 is going to be going from liquid to solid. Well, if liquid is that red line and the solid is the green, then 2 is going to be going backwards in that same spot. Going from liquid to solid is called freezing. And yes, there's a scientific name for this that we'll use later called solidification. Probably use the common names most often, but there's going to be a case where you need to know what those words mean. Okay, now I'm releasing energy when I go backwards on this curve. So that means it's exothermic. All right, liquid to gas. Okay, so that would be up here. That's called boiling. Boiling or evaporating. Or vaporizing. Vaporization. Okay. That's also going to be endothermic. Just going to abbreviate endo. Okay, gas to liquid, going backwards right there. Gas to liquid. That is called condensation or condensing. Okay, there's no other name for that. That's actually the scientific name. And it is also exothermic because I'm going backwards on this curve. Now, there are two of them that you don't see very often, and that is at the correct temperature, you can go directly from a solid to a gas. So I could go straight from a solid to a gas, or from a gas to a solid. Now that has to be under the right conditions. Okay, we want to know the names of those. Going from a solid to a gas is called sublimation or subliming. Going from a gas to a solid is called deposition or depositing. Okay, sublimation from solid to gas, again, that would be endo. And from a gas to solid, that would be exo. All right, on sections A, B, and C, D, and E, F, I want you to note A, B, C, D, and E, F, those are the ones where we have kind of an upward slant. The temperature is changing, okay? The kinetic energy increases because as energy is added, the temperature increases, which means the particles move faster. So note that the y-axis increases on those, right? That's why there's an upward slant, because there is an increase in temperature at those points. But then you notice in section BC and section DE, there's no change in temperature. The potential energy is increasing, not kinetic. So up here it was kinetic energy. We have molecules moving faster, so the motion is increasing. In sections BC and DE, the potential energy is what's increasing, because as energy is added, the temperature remains constant. It does not change, which means that energy is not used for raising the temperature. It's used for breaking IMFs, intermolecular forces. And that's why there's a flat line there. All of that energy is put into separating the molecules and changing the state of matter. The temperature doesn't change. That happens at the melting point, freezing point, boiling point, condensation point. Okay. Melting or boiling, the melting point or freezing point is the temperature at which solid turns into liquid or liquid turns into solid. Solid turns into liquid, again, that's melting. Or liquid turns into solid, which is what we normally call freezing. Boiling point or condensation point is when the liquid turns into the gas. That is called boiling. Or the gas turns into the liquid. That's condensation or condensing. For water, these are pretty common numbers. The melting point or freezing point for water is 0 degrees Celsius. And if you think in terms of Fahrenheit, it's 32 degrees Fahrenheit. By the way, what's that in Kelvin? It's 273 Kelvin. Okay. The boiling point or condensation point of water, that's where it boils, that's 100 degrees Celsius. Or if you want to know in terms of the Fahrenheit system, it's, I think, 212 degrees Fahrenheit, which is 373 Kelvin. All right, so let's label this. We want to label where the solid, liquid, and gas are on the graph. So I'm going to just put an S, L, and G. Okay, solid is there. As long as the temperature is increasing, I've got one state of matter. The liquid is right here, and the gas is right there. We want to label where melting and freezing happen on the graph. Well, melting be going that way, and then freezing be going that way. What's the melting point of the substance? Well, the melting point is the temperature at which the melting occurs. So that would be right about there, 40 degrees Celsius. What's the freezing point of the substance? It's the same temperature. The only difference is whether we're heating it up or whether we're cooling it down. Since it's the same temperature, we would just put 40.0 degrees Celsius for the freezing point as well. Again, the difference is just whether we're cooling down or warming up. Is melting endothermic or exothermic? Well, as long as we're moving that way, where heat is being added to the system or absorbed by the system, it's endothermic. As long as we're moving that way, where heat is being released by the system, it's exothermic, where it's being removed from the system. All right, hope that's helpful. You should have everything you need to finish the practice from the heat theory lesson.